Hello friends, today we are going to discuss the questions, and the questions are from the year 2013, and they are total of I think 9 questions. And this is inclusive of mains as well as advanced. In the first question, it was asked in the 2013 mains, and it states that a beam of unpolarized light of intensity I naught is passed through a polaroid A and then through another polaroid B, which is oriented so that its principal plane makes an angle of 45 degree relative to that of A. The intensity of the emergent light is. So in this case, we have two polaroid A and B. So let us draw an approximate figure for that. So this is our polaroid A, and polaroid B is said to be at an angle of 45 degree with respect to polaroid A. Okay. So this is our vertical axis, and we are going to have at angle of 45. So this will be our polaroid B, and the initial intensity, that is of I naught, is first passing through our A polaroid, then it is going to pass from the B polaroid, and this I naught is unpolarized light. So first let us discuss how the polaroid A is going to affect this I naught intensity, and we can say from that as polaroid A and polaroid A is going to reduce the intensity of the transmitted light by a factor of 1 by 2. Okay. So here let us suppose we call this as IA, then this IA will be equal to half of I naught. Okay. So it means this is the output of the polarized A. Then this IA is going to pass through a polaroid B, and in that case let us suppose the intensity is given as IB, and this IB will be, let us say, polaroid B, and polaroid B is going to give us an output of IB, and that will be equal to our IA and cos of square and the angle theta, which in this case is about 45 degree. So we substitute the value, we get our IB will be equal to IA is our half of I naught multiplied by cos square of 45, and which gives us I naught by 2 multiplied by 1 by 2, and this comes as that IB will be equal to I naught by 4. So therefore the option C is the correct option. Option C is correct. Okay. So we come to the next question, and this question was also asked in the year 2013 mains, and it states that the diameter of a plano-convex lens is 6 centimeter and thickness at the center is 3 millimeter. If the speed of light in the material of lens is 2 into 10 to the power 8 meter per second, the focal length of the lens is. So this is, we can say, based direct in the formula, and we can find out the focal length by using the formula that our 1 upon f will be equal to refractive index n minus 1, and it is a plano-convex lens, so we can just write it as 1 upon r. Ideally it is 1 upon r1 minus 1 upon r2. Okay. And first of all, we are going to find out the refractive index, that is of n, and n is equal to the speed of the light and ratio of speed of light and the ratio of the velocity of the light in the material, that is, it is c upon v. C we know is into 3 into 10 to the power 8, v is given as 2 into 10 to the power 8. The refractive index comes as 3 by 2. Now we have to find out the radius of curvature, and we know the relationship between the radius of curvature and the thickness at the center. Okay. So you can say a radius of curvature that is of r, and we can write the relationship that our t is equal to our d square divided by 8r. Here t is the thickness at the center, and d is the diameter. So therefore we can write from here that our r will be equal to d square divided by 8t, and d is given us to a 6 centimeter, so we can write this 0.06 whole square, and 8 multiplied by t is given as 3 millimeter, and that will be coming as 0.003 meters. So radius of curvature will be coming as 0.15 meters. Now we can just use the formula that we have 1 upon f, and refractive index is 1.5 minus 1, and this is 1 upon 0.15, and this gives us that the focal length f will be approximately equal to 30 centimeters. So option number C is the correct option. Option C is correct. Next question, it was also asked in the 2013 mains, and it states that two coherent point sources S1 and S2 are separated by a small distance delta as shown. The fringes obtained on the screen will be. In normal, you can say, two coherent sources experiment, these sources are placed vertically aligned, but in this particular question they are aligned along the horizontal axis, and the distance between them is given as delta. Okay? And the screen is at the distance d, capital D rather, from the source S1. Okay? And so we have two sources S1 and S2. So each point source, whether it is S1 or S2, is going to emit a spherical wavefront. So we can say that each point source S1 or S2 emits a spherical wavefronts. And it is given that they are coherent, so we can say the wavefront interferes to form a visual pattern. And we can say when coherent, these wavefront interfere to form a visible pattern. And for that we can just also can use to find out the what kind of pattern it might be, we can use the principle of superposition. You can say superposition principle. And so at any point the resultant intensity can be constructive or destructive depending upon the path difference. So you can say the resultant intensity at any point is due to constructive or destructive. Interference depending upon the path difference. So therefore we can say the path difference, which is represented as delta for any point on the screen, point on screen, we can write that as delta of x will be equal to R2 minus R1, where this R1 and R2 are the respective distances from source S1 and S2. R1 and R2 are the distances from S1 and S2. And for bright fringe, we know that our delta of x should be equal to n times lambda, where this n is our 0, plus minus 1, plus minus 2, and so on. And similarly for dark, which is destructive interference, dark fringe will be giving us delta x is equal to 2n plus 1, and we have lambda by 2. So therefore we can find out what will be the locus of the fringe. Fringe locus. And so the points which are having the same path difference are going to lie on the circle, because R2 minus R1 will be a constant factor. And like I said in the starting, that each point will be generating a spherical wavefronts. So if the path difference is constant, or path difference is same, then the locus will be lying on the you can say in the circle. Therefore we can write that points with same path difference lie on the circle as of R2 minus R1 will be a constant. So based on this, we can say that the fringes are concentric circle. Fringes are concentric circles. And centered on the axis equidistant from the sources. Centered on the axis equidistant from the sources. Okay, so it will be concentric circles. So we can say that option number D is the correct one. Option D is correct. So we can go to the next question, and it was also asked in a 2000 mains, and it states that the graph between the angle of deviation delta and the interference I for a triangular prism is represented by. Okay. And basically this graph is U-shaped. Okay, so and concave is, you can see, upward, and the point of minimum deviation will be equal to I is equal to Im, and the delta is equal to delta m. Okay. So for this particular point, we can say our I is equal to our Im, and giving us delta is equal to delta m. So this is our, you can say, quite straightforward graph, that the option C is the correct one. Option C is correct. Next question, and it was asked in the year 2013 advance. Okay, and it states that in the Young's double slit experiment, using a monochromatic light of wavelength lambda, the path difference in terms of the integer n corresponding to any point having half the peak intensity is. Okay, so we have to find out the half the peak intensity. Okay. And the standard formula for the peak intensity is, you can say, for the intensity at any point on the screen that is given as I which will be equal to I naught, and we have cos square delta phi by 2, where I naught is maximum intensity with a path difference of n lambda, and delta phi is the phase difference. So our I naught is maximum intensity and with path difference n times lambda, and our delta phi is our phase difference and we also know the relationship between the delta of phi and you can say the path difference, that is our delta of x. So you can say phase difference, this will be equal to 2 pi by lambda and multiply by delta of x. Therefore we can write that the intensity I is of I naught cos square, and this comes as pi delta x upon lambda. Now we have to find out the half peak intensity. Half peak intensity, which means our I is equal to I naught divided by 2. So we substitute it, we get I naught divided by 2 is equal to I naught cos square, and we have this as pi delta x upon lambda. I naught goes with I naught, and this gives us that cos square pi x delta x upon lambda is equal to 1 by 2. And from here we can write that our 1 by 2 will be equal to, sorry, not 1 by 2, we can write our pi delta x upon lambda is equal to pi by 4, and pi by 4, and so on. Therefore the path difference delta of x will be equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on. Okay. And if we want to write it in term of integer, that is our n, so we can formulate it that in terms of integer n, we can write that delta of x is equal to n plus 1 half and lambda by 2. And this can be further written as 2n plus 1, and we have this as lambda by 4. So the option number B is the correct option. Option B is correct. So we come to the next question. So this question was asked in the year 2013 advance, and it states that it is a, you can say, match column 1 with column 2, and it states that a right angle prism of refractive index mu1 is placed in a rectangular block of refractive index mu2, which is surrounded by a medium of refractive index mu3 as shown in figure. A ray of light E enters the rectangular block at normal incidence. Depending upon the relationship between mu1, mu2 and mu3, it takes one of the four possible paths EF, EG, EH or EI. Match the paths in the column 1 with the condition of refractive indexes in the column 2 and select the correct answer using the codes given below in the list. So in this case we have a prism and it is placed in a rectangular block. Okay, so this is a rectangular block and a light is incident, that is of E, and there are total four options in which this light E can be manipulated by the prism. You can say a combination of prism as well as the rectangle block. But since the incident ray is perpendicular to the rectangle block, nothing much can be done by the rectangle block excepting making it through go at a perpendicular angle. And so entire manipulation will be done by the prism depending upon the refractive index combination. So here the three are the which pass through the, you can say, prism as well as the block to the right side, and one is the total internal reflected, that is our eye. Okay. So let us say that we are given that light ray, which is our E, it enters rectangular block normally. Therefore, no refraction at entry. No refraction at entry. And inside the block we have a prism, and the ray interacts with the, you can say, two surfaces. One is our prism block and the one is the outer surface, that is block and outer medium. And okay, so we can say ray interacts with two interfaces. The first interface is prism block interface. Prism block, and where we have mu1 as the refractive index of the prism, and we have mu2 as refractive index of the block. And second is the block and the outer medium. Block and outer medium. And block and outer medium, mu2 we already know that it is a refractive index of the block, and mu3 is the refractive index of the outer medium. So ultimately all the combination, or you can say comparison, of refractive indexes is going to define how the ray is going to follow, whether it will be refraction or it will be total internal reflection. Okay. So let us discuss the paths one by one. So first path is our E and F. So we have a path EF, and that is our option P. And at the prism surface, it bends towards the normal. Okay, this is normal, so we can say it is this EF is bending towards the normal. So let us call this as interface 1 and this as interface 2. So we can say at interface 1, ray, that is our EF, bends towards the normal. Towards the normal. So therefore we can say that the refractive index of mu2, that is for block, is greater than for our prism. And at interface 2, this EF bends away from the normal. Bends away from the normal. Okay, so if this is a normal at EF, at the block and air interface, that is interface 2, EF bends away from normal. So therefore we can write that our mu3 is less than mu2. Okay. So we can just write all these both answers. So we can say our mu2 is greater than our mu1 and our mu3 is less than our mu2. Okay. So P is going to give us a option number 2. Okay, so you can say P is with this belongs to P. Now we come to the next ray, that is our Q, a Q option, that is of EG. We have ray EG and that is our option Q. So this matches with second. So option Q, or rather we can say ray EG, it does not bend, move straight. So we can say no bending and no bending at either interface. And we can also say that ray continues undeviated. Continues undeviated. So therefore all the refractive index is mu1 is equal to mu2 is equal to mu3. So Q is going to be option number 3. So this belongs to Q. So we have this belongs to our 3. And next is our path EH. And which belongs to our ray, sorry, it was ray EH. Ray EH, or we can say the option is our R. and the ray bends away from the normal at interface 1. So at interface 1 we have ray bends away from the normal, So therefore our mu2 is less than our mu1. And then we come at interface 2, and at interface 2 this also bend here away from the normal. Okay. So ray bends away from normal. So under this condition we can say that our mu3 is less than mu2. And for okay, we can also find out another option for total internal reflection. Okay. That will sort it out more. So you can say, but no total internal reflection. So from here we can say that mu1 sine of 45 is less than mu2 sine of 90. So this gives us that our mu1 is less than square root of 2 times mu2. And we can just combine all these options. So we get mu2 is less than mu1, and we get our mu3 is less than mu2, and finally we get that the mu1 is less than square root of 2, and this is mu2. So therefore we get option number 4, that is for Q, this is R. So therefore option number D is the correct option. Need not to find out for S. So we get option D is correct. D is correct. Next question. It was also asked in the 2030 advance, and it states that the image of an object formed by a plano-convex lens at a distance of 8 meters behind the lens is real and is 1/3 the size of the object. The wavelength of the light inside the lens is 2 by 3 times the wavelength in the free space. The radius of curved surface of the lens is. So here we are given that the image is real and 1/3 the size of the object. So indirectly we can get the magnification. Okay. So we start from there only. We say that our image is real and this is 1/3 size of object. Therefore magnification, that is rm, will be equal to 1 by 3 and with minus sign because of the real image. Okay. And we are also given that the image distance is our 8 meter behind the lens. Okay, so we can just draw a figure also, it would bring clarity to that. This is our plano-convex lens, and we have this some kind of object, and the image is being formed will be here at a distance of 8 meter, and the object is okay. Anyways, we can just start the object because of the magnification. So this will be 24, but not a big issue. So this is our object and this is our image. So we can just calculate it also. So our m is equal to v upon u, which gives us minus 1 by 3. Which is equal to minus 1 by 3. So this gives us this gives us that our u is equal to minus of 24 meters. And wavelength inside the prism lens is given at 2/3 time. From here we can find out the refractive index. We can say our refractive index of lens, if given as mu excuse me, which will be equal to wavelength in the air and wavelength in the lens. So we get this as air is 1 and this is about 2 by 3. So refractive index is about 3 by 2. Now we can use our lens formula rather, or we can say that our 1 upon f is equal to 1 upon v minus 1 upon u. And the focal length is we need to find out. So this comes as 1 upon 8 and minus of minus 1 upon 24. This gives that the focal length is our 6 meters. And we have to find out the radius of the curvature. And it's a plano-convex lens, so one radius of curvature will be infinity. So we can write that 1 upon f will be equal to mu minus 1, and this comes 1 upon r minus 1 upon infinity. So we just found out it is 3 by 2 minus 1 and 1 upon r, and this will be equal to 1 upon f, that is 1 upon 6. So we get our r is equal to 3 meters. So option number C is the correct one. Option C is correct. Next question, and it was asked in the 2030 advance, and it states that a ray of light traveling the direction I plus root 3j by 2 is incident on a plane mirror. After reflection, its travel along the direction I minus root 3j divided by 2. The angle of incidence is. So first of all, we can draw an approximate figure for that. So suppose this is the plane surface and we have incident light, and the equation is given as I plus root 3j and divided by 2, and it will be reflected in this direction, whose equation is given as I minus root 3j and divided by 2. So let us suppose this angle is theta. Obviously this angle will be also theta. Okay. And the angle between the incident and the reflected, this angle will be our 180 minus 2 theta. So now we can use the straightforward formula that cos of 180 minus 2 theta will be equal to the dot product of two vectors. Okay, so we have in the numerator I plus root 3j whole divided by 2 dot I unit vector root 3j and whole divided by 2, and then in the denominator they will be respectively there, you can say their magnitude. So we get this as 1 by 2 whole square plus root 3 by 2 whole square and its square root. Similarly for other part also we get this as 1 by 2 whole square plus minus root 3 by 2 whole square and square root. Now it is a simple calculation, and this is going to give us that our cos of 180 minus 2 theta will be equal to minus 1 by 2. And from here we can write that 180 minus 2 theta will be equal to our 120. This gives us that 2 theta will be equal to 60, giving us that theta is our 30 degree. So the option number A is the correct option. Option A is correct. Come to the next question. It was also asked in the year 2013 advance, and it states that using the expression 2d sine theta equal lambda, one calculates the value of d by measuring the corresponding angle theta in the range of 0 to 90 degree. The wavelength lambda is exactly known, and the error in theta is constant for all values of theta. As theta increases from 0 degree, so we have to find out what will be the absolute error, or we can say fractional error in d. So we have to express d first of all in terms of the lambda as well as theta. So we start with the given expression. We are given that 2d sine of theta is equal to lambda. So from here I can write that d is equal to lambda upon 2 sine of theta. And we just try to sort it out because we are going to differentiate it. So let's take natural log on both sides, so that will clearly help us. So we get natural log of d is equal to natural log of lambda minus natural log of 2 minus natural log of sine of theta. Therefore, we get this as delta d upon d is equal to lambda is given, it means a constant, and 2 is obviously constant 0. This comes as minus, and we come this as cos of theta divided by sine of theta, and we have this as a delta theta. Therefore, we can write this will be equal to minus cot of theta, and we have the delta of theta. And if you are mainly interested in the magnitude part, so therefore we can write delta d upon d, and its magnitude will be equal to cot of theta and delta of theta. And in the question it is given that theta increases from 0 to 90 degree, so obviously cot of theta is going to decrease. We see theta increases from 0 to 90 degree, This means that our cot of theta is going to decrease, and it is mentioned that delta of theta is constant. So you can say our delta of theta is our constant. Therefore, we can say the fractional error in D decreases as theta increases from 0 to 90 degree. Okay. So fractional error D decreases. So option number D is the correct one. Option D is correct. So I think this completes all the questions. Yeah, so these complete all the questions of year 2013 mains as well as advanced. Thank you.